Okay, so in this video we'll be talking about roots of complex numbers. And what are roots of complex numbers? Well, we're really just going to be solving an equation of this form where we have z to the n equals c. And c is just a complex number here. Okay, so c is an element of the complex number set, and n is an element of the positive integer set. Okay, and notice that c can be written as x plus yi here. So what we'll be solving for is we'll be looking for the roots of this equation. The solutions to this equation are the nth roots. The nth roots of the complex number c are the n solutions of z to the n equals c. So what that means is if we have a question like find the fourth roots of 1, that really means solve z to the fourth power equals 1. And we're looking for the value of z, okay? So we're looking for the complex numbers that when I raise them to the fourth power, I will get 1. And there should be 4 solutions here, okay? If I had find the cube roots of 8i, 8i is a complex number, we can set up the equation to look like z cubed equals 8i. And again, we're looking for z, okay? So we're trying to solve for the complex number when I cube it, I'm going to end up with 8i, and there should be 3 complex numbers that can do that. And just here's another example. Find the 6th roots of 4 plus 3i. 4 plus 3i is our complex number. I'm looking for z to the 6th equals 4 plus 3i. Okay, I'm looking for the z value there. And there should be 6 solutions. So let's look at the properties of this, of the roots of complex numbers. So there are always going to be exactly n number of nth roots. So if I had 4th roots, I would have 4. If I had cube roots, if I was looking for the cube roots of c, I would have 3 roots. All right. And if the complex number that I'm looking at, whatever my c is, if c is actually just purely a real number, the complex roots will always come in conjugate pairs. And if c is not a real number, for instance, if it was 8i or it was 4 plus 3i, the complex roots will not all come in conjugate pairs. Okay? The roots of z to the nth power will always have, or all of the roots, all of the z's that whatever my solutions are, they will all have the same modulus, and the modulus will really just be the modulus of c raised to the 1 over nth power. And this is really due to De Moivre's theorem, okay? This part right here is part of De Moivre's theorem. We'll look at why that happens in a little bit, but you can write that down for now. On an Argand diagram, the roots will all lie on a circle with the radius of modulus c raised to the 1 over n power, okay? And that's really because all of the roots will have the same length, right? And also, the roots will appear, if I were to graph all of these on the Argand diagram, the roots would all lie on the circle and they would all be equally spaced on the circle, which is kind of interesting, okay? You can see that in this example, this would be if I was looking for the cube roots of some complex number. Each of those roots would have a vector that looks like this on the Argand diagram, and they would be equally spaced. So notice here that because they're cube roots, they're spaced at 120 degrees apart. Okay, if I had 4 roots, they would all be spaced 90 degrees apart. Okay. All right. So let's look at how we can solve these equations. Now that we know what those roots are and what they'll look like on the Argand diagram, let's look at the process for actually finding these. If I have z to the nth equals c, or z to the nth equals x plus yi, those are the same. Okay, those are the same equations. There are two ways to do this, and the first way would be to factor. Right? If I was going to factor this, that would be one way to do it, but it's not ideal because it's only limited to real numbers. Okay, so it's only useful for finding roots when c is a real number, or basically when this y component, the imaginary component, is 0. Right? The second method that we're going to look at is the nth roots method, and this method always works, whether c is real or imaginary or complex. And the nth roots method relies on polar form and on using de Moivre's theorem. Okay. Specifically, the steps are basically we have c. We're going to take it and get it into polar form, which is the r cis theta form. And once we have c, we're going to use the property, once we have the polar form, we're going to use the property of the unit circle where cosine and sine repeat every 2 pi, and we're going to use the property where cis of theta is cis of theta plus 2 pi k, where k is an integer. That's not necessarily positive, so let me just erase that part there. Okay, k is an integer value. And then once we have that, we'll use de Moivre's theorem, and basically we're going to get z by itself. Okay, we're going to get rid of that exponent here. So normally we'd write it, we would have de Moivre's theorem where we raise a complex number to the power of some number. But in this form, we would have the polar form on this side, and we would undo the n here by taking the 1 over nth root, or raising both sides to the 1 over n power. And what that does is it gets my polar form, my complex number, and it takes the magnitude, right? This is de Moivre's theorem. It takes the magnitude, raises it to the 1 over n power, and takes the angle, or the phase, the argument of z, or this complex number, and it divides it, or multiplies it by the exponent, which turns out to be 1 over n, so we're really dividing by n. Okay? And then we end up with z by itself. So notice here that this is the solution. This is the solution to our original question, which is find the roots of this situation. Okay? But notice that we have a k here, and so k being integer values, we have to start plugging in values into k to find all the possible solutions. Okay, so this would only be the general solution. We would have to find the specific ones that fit our case. So we would use n consecutive values of k, usually starting from 0, okay, all the way through n minus 1. So for instance, if I said find the 4th roots and n was 4, okay, if n was 4, then we would use probably k equals 0, 1, 2, and 3. So we'd go all the way to n minus 1. Notice that the number of times that I substitute the k value in is equal to the number of roots that I have. Okay, and that makes sense because of this this property right here that we talked about. There are exactly n nth roots of c. All right.